Let's get started. I want to welcome everyone and thank you for being here for today's VDE Tech Talk, Project ICECHIP initial results and implications for a hail PV risk assessment. My name is Dennis Weaver. I'm a meteorologist on staff with VDE Americas, and I am very excited today to be joined by two of the world's leading experts in hail risk and get their insights on this project this field project from last summer. But first, just a quick note on VDE Americas. We are a fully owned subsidiary of the VDE Group, which is one of the largest technology organizations in Europe. VDE Americas focuses on providing technical advisory and risk mitigation services to the solar industry and is also recognized as one of the world's leading experts in solar project risk analysis and loss prevention, which is, of course, the subject of today's talk. Project ICECHIP was, as I mentioned, conducted in the summer of 2025. It stands for the In-situ Collaborative Experiment for Collection of Hail in the Plains, as you can see in the image on the right, the aerial extent that was covered by this project, and it was the first extensive field study of hail-producing severe storms in nearly 40 years. I'm going to learn much more about this from our presenters today. But first, in terms of introduction, I want to welcome our guests. First, Dr. Rebecca Adams-Seelan, who is the lead principal investigator for Project ICECHIP and principal scientist at the Atmospheric and Environmental Research for the Janus Group, as well as an affiliate faculty member at Florida State University and the University of Wisconsin-Milwaukee, as well as Dr. John Allen, who is a professor of meteorology at Central Michigan University, as well as an associate director of the National Science Foundation's Artificial Intelligence Institute for Environmental Sciences, also a principal investigator for Project ICECHIP. So two of the very best with us today. At a high level, we'll talk just a bit about what ICECHIP was, when, where, and how, as well as the instrumentation that was used to collect hail data, how that differs from previous older methods, and then ultimately what this means for hail risk assessment for PV plants. There'll be a short kind of section from each presenter to talk about some of their results and findings. We'll have a collaborative discussion section, and then at the end, open it up to audience questions. With that, I'm very happy and pleased to turn it over to Dr. Adams-Seelan.
All right, thanks, Dennis. I appreciate it. Great to be able to speak with everyone today. Right, so as Dennis mentioned, talking about ICECHIP today, as he said, In-situ Collaborative Experiment for the collection of hail in the plains, funded by the National Science Foundation. Important thing up front with this is that there were a total of 19 different institutions involved. You can see their logos splayed out there. That includes a whole range of universities across the US, some private companies, some insurance collaboratives like IBHS, 4 different countries. So this was not done by any of us in a vacuum. I think we had a total of not quite 100 people in the field. So this is really a very large focused effort. Next slide, please, Dennis. All right, so what was our goal of ICECHIP? As Dennis mentioned, it had been 40 years since the last major US-focused field campaign on hail, so we had a lot of ground to cover. But there had been some convection-related field campaigns in the past. You might be familiar with some of the tornado-focused ones, like Vortex maybe, but nothing specifically focused on hail. So one of the primary things we wanted to do was measure the whole life cycle of hail. We wanted to understand everything from where it forms in the storm to how it reaches the ground and everything in between. So that includes observing not just the storm itself, but also the hail at the ground, not just once, but multiple times, not just things like size, like you get out of hail reports, but things like concentration, density, the speed at which it falls, the impact it has when it reaches the ground, as well as characteristics about the storm itself, things like what does it look like on radar, the updraft structure. So we wanted to get basically everything we can, so we can both get our observations at the ground of hail characteristics that subsequently directly impact damage, but also we can attempt to try to predict those things by all our observations with the storm, so we can understand what's going on there. Now, this may not sound that like, well, duh, you're wanting to understand how hail forms. Just observe it and observe the storm. I mean, that sounds very simple, but it's turned out to be more complicated, as is usually the case with science. And that kind of explains somewhat why it's been 40 years, is that there's a lot of technology to be brought to bear here now. So how are we going to do this? Well, our plan, fingers crossed, was that we were going to spend 6 weeks in May and June of 2025 in this yellow bound in the Front Range in the Great Plains. And we thought, we can probably, during that 6-week period, we're hoping we can deploy on what we call IOPs, intensive observing periods. But another way to say that is hailstorms. We thought, yep, there's probably going to be 20 hailstorms that we can reach and get some observations of. So did we succeed? Next slide, please, Dennis. Yes, we were extremely fortunate in that 2025 was an active year, and we were lucky kind of even beyond what we had dreamed. So we had a total of 24 hailstorms or IOPs. Here on the right, every one of these little white dots is one of our IOP locations. So you can see we went all the way from just north of the Mexican border to just south of the Canadian border. And we managed to get just a whole geographical range of hailstorm locations. 22 of those had at least some hail observed with them. We saw a wide range of different sizes. 18 of those, we saw hail with a maximum size of at least 25 millimeters or 1 inch. We managed to get 2 of them with hail max dimensions larger than 100 millimeters or 4 inches. One of them was even larger than 6 inches. So we got the full gamut. But as I mentioned earlier, max hail dimension or diameter that's not the only thing we care about. We care about things like concentration and density and the storm itself. So we got to see things like drifts of drifts on the side of the road of a whole bunch of very small hail, compared to some of these storms where we saw extremely large hail. Some of them produced a lot of extremely large hail. Some of them produced only a few bits of extremely large hail here and there. So the varying concentration was important. And sometimes those happened even within the same storm, where it had drifts of hail followed by 6-inch hail. So this was a really fantastic data set. In terms of storm types, we saw a range of storm types too. We learned that hail can be produced by a wide range of different types of storms. For example, what we might call cellular or linear systems, where cellular meaning the storms are isolated. There's maybe just one on its own, or if there are more than one, they're separated. Versus linear, we have a whole line of storms that are producing some hail, or maybe the storm has a bunch of convection, bunch of thunderstorms. They're all kind of mushed together. We can call that multi-cell. We saw hail from all of these. We saw hail from storms that would maybe merge but from one form to another. We also saw stuff with co-located flooding, which was surprisingly frequent. But again, we found it was extremely important to observe this wide range of different things, not just one type of storm. We weren't only hunting out, let's try to find the largest hail we can. We wanted to try to observe as much different type of hail, because damage comes from a wide range of hail. It doesn't just come from 6-inch hailstones. So we wanted to see the full thing. I'll also note, we ended up with over 15,000 miles of driving. So bless our poor rental companies that provided those vans. Next slide, please. All right, so I mentioned new technology available. We were it's been 40 years. So yeah, we had a whole range of novel measurements in the field, and I'll mention some, and John will talk about some more. But starting in the upper left, and I'll go from left to right, The one labeled CMU with a little balloon, those are wind songs. Those are basically temperature and wind profiling systems that you can release with a party balloon. We had a whole bunch of those. Next one labeled AER, that is a hail pad, which is basically a piece of insulation you put on the ground. I think John saw maybe, I don't know, like 6,000 or something of these things in his driveway. So these were deployed all over the place. Low tech still was around in the 70s and 80s during the last campaign, but it works, and you can get the full size distribution of hail that reached the ground at that point, which again, we want to know that full size distribution, not just the biggest hailstone. Next one is IBHS. That's a 3D scanner. So you can actually get the hailstone in the field, do a very quick 3D scan of it, and now you've got a three-dimensional shape of your hailstone. That is important for, I think Dennis is going to mention this later, if you're wanting to do testing of impact testing, it might be nice if you can do impact testing of actual hail-shaped things instead of, using actual hail-shaped missiles as opposed to just spheres, because hail isn't really just a sphere. Next image, the CMU, that's crushing. John's team actually in IBHS did crushed thousands of hailstones in the field to determine their compression strength in addition to triaxial measurements, again, important for impact-based characteristics. Final picture on the upper right labeled ABOM, that's called a hail sonde. This was designed by the Australia Bureau of Meteorology. It is just what it looks like, a tiny little styrofoam ball that has a sensor in it, but you release it into the storm with a balloon, and it acts exactly like a hailstone in that it advects around by the storm, it accretes water on it, and it freezes on it, and then it eventually falls back out at the ground, and they can receive all this information to know, hey, where could potential hail be going in the storm? What might these things look like, or these trajectories look like? And for that matter, how fast is the updraft moving? This is all a key kind of in-storm information that you can't really get any other way. Because we can't, they're not flying anything through a hailstorm. Second row, all the way on the left, the one labeled AER NCAR, that is the NCAR cold lab in Boulder. So it stays at -20 Celsius year round. We have, I think, 26 boxes of hail there from ICECHIP, but that allows us to do some more thorough 3D scanning using photogrammetry techniques. It also allows us to do cross-sectioning and examine the layers to see, oh, hey, what kind of growth is going on in the layers of the hailstone. We can do things like isotopic analysis, where we sample very small bits of each layer of the hailstone and can do chemical analysis, basically, that tells us the temperature at which that layer froze, giving us placement of the hailstone aloft. The moving image is a tumbling hailstone going across a very high resolution, high frequency camera. So that's exciting in that we can come up with, we can track the hailstone, we can estimate its two-dimensional shape, but we can also track its horizontal and vertical velocity as it moves. I'll talk more about that in a minute. Next image labeled CU, that is a drone, kind of a longer-lived fixed-wing drone where they actually flew over the hail swath and were able to take measurements and determine the size over which the hail swath would extend. And then finally, all the way on the lower right is mobile radar, because this is key to understand, hey, what does the storm look like on radar and how can we actually attempt to forecast these things? And I think I'm probably well past my time here already. But Dennis, can you go to the next slide? Actually, let's just skip one more to IOP4, because I know John's going to talk about this. There we go. Okay, so this is one specific IOP or storm that we deployed on in general. You can go ahead and hit play. You'll notice all the text lined up and down. That's everywhere where we deployed instruments. Now the little green and purple dots moving around, that's the people going out to deploy them. So that's exciting, but not quite as important. But the key part here is you can see, oh, we deployed all our instruments in a T around Roaring Spring, Texas. The radar reflectivity shows the storm moving across the T. This was a fantastic storm, both in terms of hail collection. We managed to get up to, this was one of the storms where we got up to 140 millimeter measurements of hail, but also some hail drifts on the side of the road. Hundreds of hailstones were collected, measured, and strength tested. We collected 4+ coolers of hail and transported them back to the cold lab. And there was a hail sun released in the storm that measured an updraft speed over 150 miles per hour, which was much faster than anything had ever been observed before, making us think, oh, we've been underthinking how fast these updrafts are for decades. Next slide, please. All right, what can we do with this information? And just keep clicking through here. So with this hail camera, for example, you can keep clicking, Dennis. We get a whole bunch of images, 11 million, in fact. And some folks on my team designed a machine learning algorithm to try to classify these. For example, the 3 on the upper left are very much not hail. The rest of them are hail. Trying to teach the computer that turned out to be fairly difficult, but it had happened. So next slide. This is kind of the exciting bit that we're just now getting to. The thing on the left is tracked hailstones from that camera with the vertical velocity on the y-axis and the horizontal velocity on the x-axis. So now we know not only, hey, how fast were these hailstones falling, but what horizontal speed were they moving across the camera view, which can get us at the angle at horizontal, or the angle from vertical at which they might be falling. What I found interesting here, each of those different colors represents a different camera that was deployed in different places across the IOP. And you can see that whether the hailstones were falling, from the east or from the west, that's what the horizontal velocity corresponds to, can completely change depending on where you are in the storm and what time the storm was producing the hail and which camera was seeing it. So it's not a simple matter where the hail is just always coming from one direction, but it's, like everything to do with hail, more complex than we thought. The thing on the right, we collected hailstones in a freezer, mobile freezer, at the same place where we were taking camera images. So we were able to measure those hailstones and say, hey, how fast does theory say that these hailstones are falling? And there are some differences between, hey, what did theory say and what did we actually see? So we're still trying to explore that. Right, but so I had mentioned earlier about some of the additional instrumentation we were using, as well as the impact of the hailstone at the ground. And so I will turn things over to my colleague, John Allen, to speak more about that.
Thanks, Becky. So I'm going to give a little bit of an overview here of impact astrometers. So these were the devices that you would see deployed in the array that Becky mentioned from along the north-south axis. These sensors are basically a piezometer under a hard metal plate. They are impact rated up to, as we discovered during ICECHIP, around about 100 millimeters is where the piezometer actually saturates. But they are pyramidal in shape. This is basically optimized from extensive testing. And what you end up with is a series of bit samples, voltages that are returning from your device as hailstones impact it. And so on the bottom left, you can see an example of a probe here, where we're looking at sort of a short period of data, and we can see the different hailstone impacts These are then translated into what we see on the right. This is a storm aggregate, so that's a short segment. This is the storm aggregate on the right-hand side, where we're looking at the size bins that are translated off kinetic energy observations. Now, I'll come to the limitations of that, which is some of the things that the observations in the field showed us, but this is an example of the binned impacts over the duration of the storm that you see at various different sizes. So what an impact astrometer allows us to do to say that compared to a hail pad, which tells us everything that happened through that storm, is it gives us this time-sensitive measurement to sort of know how quickly are we getting impacts, how many impacts are we getting per second, what's their concentration over a space area. These impact astrometers are 12 inches by 12 inches, so they're a relatively small footprint, but they're a great way to get in-situ samples where most instruments will get destroyed. Even hail pads aren't able to handle some of these very large hailstone impacts. They tend to actually crumble at that point. Next slide, Dennis, please. And play this. So this is the perspective of a distrometer in a storm. This is from IP12, but you can see here that we've got substantial lateral velocities associated with some of these hailstones. One of the challenges, of course, with a device like the impact astrometer is that you're measuring for something that's normal to the plate. So there is some kinetic energy variations that have to occur because of these fall angles, and that's something we're still working on the calibration thereof. But it gives you a sort of idea of just how many hailstones are actually falling of relatively large sizes. Dennis, next slide, please. So what do I get out of an array of impact astrometers? So one of the most important things here is that I'm going to emphasize you can have the impact astrometer, but it may not tell you just how big those hailstones got or their kinetic properties. We saw very large variations between storms in how the kinetic energy of the stones despite relatively large sizes. So for example, in the video we just played, the stones in that particular case were materially relatively weak and low mass. I'll show you some data shortly that sort of suggests that this presents some interesting implications for the way we think about kinetic energy. From our distrometers, if we take a whole array of these, so here we're looking at the north-south segment from Roaring Springs southwards, where we've deployed these distrometers, and we sort of look at their time-integrated experience of hail impacts. So we could look at the hail impact rate. So over the entire duration of the storm is going to be the summation of what's from left to right here. But you can see there's a period here where we see impact rates of around about 2 per second. During that period, we also see the 90th percentile of hail size up to 35 millimeters. Now, I'm going to say that this is the storm that produced the very giant hail, and in fact, this particular site, we saw damage to the distrometer's tripod, so an aluminum tripod associated with this. So we actually observed much larger hail in the collection phase than what we see in terms of the impact astrometer measurements. But what this type of measurement allows us to do that we've previously been able to do is to think about, well, okay, for how long was I experiencing hail? For, how much of and if we think about, say, an average solar array, maybe a couple of kilometers north-south, well, how much of that array would be impacted, and how much of that array might see damage to the level where we're seeing maybe full replacement versus, say, partial, right? It allows us to think about things like swaths. Next slide, please, Dennis. The interesting thing that sort of arises if we look at what we collected, which is the distribution on the top right here, that is the observed maximum dimensions of hailstones recorded during this particular IOP, and that's from all sites across here. We actually have data at each individual point at about 250 meter resolution. You can see that what you get out of the distrometer strongly depends on the kinetic energy relationships that are used. So here the distrometer seems to suggest relatively small sizes, and this is a problem common to all distrometers. Distrometers rely on the quality of the kinetic energy information that you have to fit in there. The observations we've taken during ICECHIP are going to be used to recalibrate those kinetic energies. So the hope is to be able to come up with something that is far more representative for our distrometer measurements, regardless of the source of the distrometer. These impact distrometers are rated far higher than what most commercial products are trying to do, because they're designed to be deployed right in the core of these big storms. You'll notice here that some of the masses it's quite extreme, right? We've got a stone here, stones here in excess of 600 grams. So fairly substantive hailstones, but these things are sporadic. The majority of the mode of the storm, right, is round towards some of these smaller sizes. So that has big impacts for a PV field, right? Very big hail that's sporadic is not necessarily going to destroy very many panels if that occurs over the site. Next slide, Dennis. So this is to give another example case. This is from IOP 12, another case where we got a really good cross-sectional sample here. We sampled the whole hail swath. You can sort of see that there's some fairly large maximum diameters here. We get up into the 70 mil range. The array was relatively well positioned. Next slide, please, Dennis. But what's kind of interesting that arises is despite some relatively large stones, the masses were much, much lower. So they're relatively low density hailstones. In this case, we actually find the hail pad told us something the distrometers didn't. We had an example on the bottom left here of around about a 90 millimeter hailstone that wasn't picked up by the distrometers, that wasn't picked up in collection because it actually shattered on its impact. But we still see this sort of disconnect between what you collect versus what you get out of a distrometer. So even if your distrometer is telling you, hey, you got size to this approximate diameter, that doesn't necessarily translate to what we're seeing in terms of kinetic energy. And so ICECHIP provides us with a fundamental basis to actually revisit that question and say, well, how much variation in kinetic energy are we seeing at a point across the swath from storm to storm? And that's going to have feedbacks for a lot of the distrometer measurements, but also a lot of the other products that we have out there. Next slide.
Awesome. Yes, thank you. Thank you both so much. This is really, really interesting stuff. Obviously, a really cool field campaign, and we're getting a lot of very interesting data out of it already. I think we touched on this a little bit already, but to kind of open it up conversationally to both Dr. Allen and Dr. Adam Seelan, one pretty important factor in modeling the potential impact to a PV site is this distribution of hail sizes that a storm generates, because that of course determines the number of times that a panel might be impacted and then the probability of you getting breakage across a plant. So with that in mind and sort of that pointed direction, is there anything specific that we can say in terms of the distribution of hail sizes that may be different from what we have assumed in the past or what we thought in the past? And I'll open it up to both of you, and this can be sort of conversational.
Go ahead, John. I think you've got more that directly speaks to this.
Yeah, I think one of the things that sort of struck us was the range of distributional numbers, right? So the concentration you're seeing. One of the things we've had a really poor measurement history of is concentration of hailstones at a point, and particularly that as a function of size, right? We've long assumed that the largest hailstone, when we get the largest hailstones, we have a lower concentration. In some cases, that isn't entirely true. And particularly for some of these cases that are sort of sub 100 millimeters, we were seeing quite high hit rates. Storm totals 600, 1,000 impacts. Now, not all of those impacts are going to be, say, kinetically relevant to a PV plant, but it does increase the probability, right? If you have some rate of failure associated with your panel, you're rolling the dice more and more times. So if they are close to being kinetically relevant, they may just be. We saw some of the observations in terms of concentration. We saw 4,000 impacts, and that's really in contrast to a lot of our existing thoughts were on the order of hundreds over the course of the storm.
So actually, I might jump in here real quick on that. Oh, sorry, go ahead.
Oh, go ahead. Go ahead.
I was just going to ask a quick follow-up on that and maybe summarize, make sure that I'm understanding that right, is one of the things that we're learning is even in the larger sized events that are producing the largest stones, the previous assumption may have been that you get a little bit less impact or a lower count of smaller stones, primarily due to available moisture and things like that. But that actually might not be the case, and you still might have some kinetically relevant stones at those smaller sizes.
Yeah, I think it really depends on the storm morphology.
Sure.
And there's a lot of variations we found in terms of storm morphology, which has implications for, say, you're using warning information. But I think it's that we found a lot of interesting ways to get big hail, I think is one of the things that sort of arose. And we really didn't have direct measurements of a lot of those cases previously.
Great.
I might just follow on to that we saw such a wide variety of concentrations over the course of even individual storms, even varying, John mentioned storm morphology, like as the storm evolves, or maybe it merges with another cell or something, and you could have your concentration just completely change from, super high concentration to suddenly now it's generally lower, and it just makes you kind of rethink some of previous classifications, which has said, oh, this type of storm is going to produce this large hail. Well, because you're only basing it off of one single report and one type of thing, and whereas really, it produced this whole wide range of stuff that we didn't really even know happened. So it just was very eye-opening that yeah, there's a lot more different kinds of hail out there than perhaps we had realized, and a lot more different ways to produce that hail than we had realized.
A good example, I think, comes from the 7th IOP. We had a storm which was producing regular, maybe 10-mile swath of 3-inch hail. So very, very large hail. And it underwent a structural transition. And it suddenly went from producing this very wide swath of very large hail to producing a very narrow swath of hail that wasn't as big, but was very intense over that particular area. So it went from being, 10 miles wide to maybe a mile wide that was actually seeing the hail production, and then transitioned again and suddenly started producing 2-inch hail over a relatively wide swath. And, that's over the course of tracking over Brownfield, Texas. We sampled the array in the low point and on the high point on the backside of it, and saw very large differences over relatively short distances. So it does point to being careful of assuming sort of what just because the radar state looks like this now doesn't mean that the storm couldn't evolve thereafter.
Right. I think that's a great example. And so over the course of these 20 events that you saw in the field, you had that variety of morphologies and structures, right? And they were all kind of they were producing results in different ways.
Yes.
Okay, I think we can go to another question that's really, really great information. And of course, and this was alluded to already as well, but a pretty important factor in the damage potential, especially when it comes to PV, is not just the size, but the actual kinetic energy of the stone, which in part is connected to the density. We know about these different growth methods for hailstones. So you have wet growth where supercooled liquid water takes a little bit longer to freeze. Air bubbles escape from the stone, and you get these denser, often more spherical stones, versus a dry growth process where the air bubbles get trapped and you come up with these very irregular sized or irregularly shaped stones. Are we learning much more about those properties specifically, and how that ultimately might relate to damage potential for PV?
I absolutely. We oh my goodness. Okay, on a very simple level, simply being out in the field collecting these, you can see the whole range of hailstones out in front of you, and that the wet and dry growth amongst even the distributions amongst even hailstones that fell immediately next to each other are just completely different. We learned that you can get giant layers of wet growth and you can get giant layers of dry growth, sometimes in the same storm, sometimes in hailstone, sometimes in the same hailstone, which was not expected. I think we're also, and John can probably speak to this more, we're also learning about how density and wet and dry growth, like the connection between those two are maybe not quite as cut and dried as we thought, but there's some more slosh, I guess you could say, where, oh hey, this stuff that looks like dry growth, yeah, maybe it was a little bit stronger than we thought, and vice versa. We are just trying now to get into connecting those wet and dry growth layers to like the actual vertical location in the storm via that isotopic analysis, but that's still got a little ways to go on that part. But I'm very, very excited to learn more about that. Yeah, that yes, we've seen a lot of information there. I'll turn it over to John.
Yeah, and so I mean that translated into some of the compressive strength testing when we were running through this compressive strength testing, right? Eventually, after you've crushed several thousand hailstones, you try to get a little bit of a feel for how some of them might behave, particularly dry growth. For example, a stone that is very heavy in dry growth often exhibits fracture planes. But then if you had a very thin layer of supercooled liquid water over the top of that dry growth, that stone suddenly became immensely hard. And the compressive strength was much, much higher. By the same token, we found some stones that were fully ductile. So when you put them through the maximum compression the load cell could possibly put on them, they basically held their shape and deformed. This is at 4,000 megapascal. So, the very, very strong hailstones were being found. But I think what this project really showed us was maybe we've high sampled a little bit in terms of some of the kinetic energy relationships that are out there, in terms of the overall density relationships that are out there. We found far more examples of lower density stones, or sort of moderate density stones, than we had previously. And that was a really big shift to say what IBHS has collected over a number of years, that maybe there's more of these stones occurring, but even in as Becky points out, even within the same storm, we often found there were three modes in a location. So you might have three different sets in a given location, where you have some very, very strong stones, some very, very weak stones, and some stones that sort of sit in a little bit of the middle, about 100 megapascal thereabouts. But I think it shows that we have to be very careful about making assumptions about density. And I think we can say, well, okay, maybe the densities aren't as high as we thought, right? But we might experience a few stones or a set of stones at a given location that are high density and therefore are kinetically relevant. We're hoping that, I think a lot of these observations will allow us to at least quantify to some degree the degree of uncertainty we're seeing from location to location. That's why we took so many stones out in the field.
That's really great insight. Thank you both for the good answers to that question. This one, maybe it's a little bit of a curveball, hopefully not, but we talked a lot now about hailstone size and the density characteristics. One of the primary methods by which we rely on understanding module breakage potential to PV is through lab testing, using freezer ice balls, solid balls of ice, firing those at panels until they break, and coming up with an overall resiliency characteristic. Obviously, solid ice balls are not hailstones. I think we've proven that. Is there anything else that may be a factor in terms of that connection between a freezer ice ball and a hailstone that we're starting to learn about that may be important for modeling purposes?
I will let John talk about the density of the ice ball, which is a whole other question. And I'll just speak to the shape. So one of the things that my postdoc and I have been doing for the past year has been doing 3D photogrammetric scans of about 100 hailstones, and holy crap, they are not spherical. Even something like the maximum dimension, the maximum dimension of our biggest maximum dimension hailstone, that's 6 inches across, is only maybe like 25 inches deep, because it's a big oblong. Trying to figure out how we can successfully represent a three-dimensional hailstone so obviously we don't want to represent it with just one number, the max dimension, but can we even simplify it down to 3 numbers, the 3 axis measurements? Can we, maybe not. Do we need to incorporate some sort of factor talking about how many lobes are there sticking out from the side? Because if you have longer lobes that are spaced farther apart, well, that's going to impact your impact different than if they're smaller lobes and they're put closer together. There's sort of this whole range of potential characteristics that we really need to incorporate into our understanding of the 3D hailstone shape, especially when it comes to testing. We're still trying to understand, but at a minimum, things like the 3 different axis measurements and hey, how many different lobes do we have poking out? We need to be able to work that in somehow, and that's not even addressing the density issue. So go, John.
Yeah, and I think that if we were to take a freezer ice ball and we look at an observed hailstone and we compare the kinetic energy of the two, right, for an equivalent maximum diameter, the two are not going to be equal. The freezer ice ball is going to have greater kinetic energy in most cases, unless we're dealing with a perfectly spherical hailstone that has grown at the absolute maximum wet growth, so that it has a density very similar to what that freezer ice ball is, right? What we're looking at in most freezer ice balls, most lab tests, as you can see here, it's fairly transparent ice. There may be a little bit of opaqueness, but realistically, we're dealing with a much, much higher density. So it means that there's sort of a translation between our larger hail size, our larger testing size, versus what the hailstone we experience. Now, coming to the shape question, one of the implications of shape is how that hailstone falls, what its kinetic energy can be, right? Because as I have a tumbling hailstone of some shape, that can basically restrict what kinetic energy I can get. There's been some interesting tests this summer looking at pneumatic cannon firing of non-spherical hailstones. What happens? Well, you have to really increase the velocities to get equivalent kinetic energies because the hailstone just wants to slow down because of the tumbling behaviors. The other impact is where the other side of this sort of problem is when we get to the impact of the hailstone itself on the module, right? A round hailstone of fixed uniform density is going to do, the freezer ice ball is going to do damage of one kind. Is that necessarily the same as what we see from a real hailstone with lobes, with different shattering properties, right? That's one of the things I think that really ICECHIP, has stood apart in is there's well over 6,000 hailstones we've measured to date, and there's still more coming. Sitting in the cold lab because we don't want to torture postdocs in the cold lab for too long. But those observations, that's the equivalent to every maximum size dimension observation we get from the Storm Prediction Center in a year. It's double what we had previously that all the kinetic energy relationships have been fitted based on. So these are the sort of observations that we needed to be able to tie these back to things like freezer ice balls. But I do think that there is an argument to start thinking about how we better determine the equivalency between these two sort of testing protocols. That I think is something that has been shown in the asphalt shingle world to be important, and I think is important for PV as well.
That's great. Thank you both for the insights there. One more question for me, and then we'll open it up to the audience. So if you do have questions for Dr. Allen and Dr. Adam Seelan, please utilize the Q&A. and I can open that up here shortly. But before we get to that, we've covered a lot of stuff as it applies to potential losses at PV sites. One additional factor that VDE's actually been doing quite a bit of work to try to understand is the winds during these events. And obviously those are impacting things like the energy a hailstone has when it makes contact with a panel and impacts a panel, but also the angle at which it falls. And I think Dr. Adam Seeland talked a little bit about this at the very beginning. We had that chart that showed the chaotic nature of where hailstones fall within a storm. But kind of in depth, is there anything that we are learning so far about hailstone fall angle in these systems?
Actually, do you mind going back to?
I can go back.
Thank you. Yeah, I have a slide with the different colors and the dots. Says how fast your hailstones fall. There we go. Yes. All right. So these are all the measurements of hailstones that fell during one IOP. So vertical velocity on horizontal axis and horizontal velocity on the x-axis. And what we only produced this figure a couple weeks ago, so I'm still learning. But what immediately got to me is that the horizontal velocities are approximately of the same magnitude as the vertical velocities. I had personally internally thought, oh gosh, that these hailstones are going to be booking it downwards, especially when you start getting sizable. Some of these seen here were like 30, 40 millimeters plus. That you're not going to. Those winds aren't going to have an impact, but yes, they do, and it is highly variable over the course of the system. I don't know. Yes, this IOP did see some strong winds with it, but I particularly in some of the, or in two of the observation locations, there it wasn't extremely strong. So that this wasn't like this massive wind producing system, but it still had some high fall angles and some pretty high horizontal velocities associated with it. So that really just opened my eyes to what was out there.
And I think overall, this is certainly something we wanted to measure during ICECHIP. The cameras provide a great way of sort of doing that, along with some of the radar, the vertical pointing radar products that we had out there in the field. We also had a whole series of impact cameras on the impact astrometer, like the example I showed earlier, where we can actually do some image work to sort of understand some of these fall angles and the variation. I think the critical thing here is vertical falling hail seems to be the exception rather than the norm. And that has big implications for what we see in terms of a lot of the stowage strategies, right? The implication of a hailstone falling somewhat from the vertical and quite substantially from the vertical is that's reducing the effective tilt stowage effect that reduces the kinetic energy that we see to a panel. And so, we saw instances here. And the other thing to remember is it's not just the winds. There are other effects that are contributing to how hailstone falls, right? If the storm has a circulation associated with it, it can come in with some sort of angle. It can also affect, we can also have things like how the stone tumbles or spins generates a Bernoulli effect. And so we see significant deviations, and we've been doing some modeling looking at just how significant those are, and particularly for larger hailstones, they may lead to much larger fall angle variations than what we first thought. So I think there's a lot of good data here that's going to be able to at least say something and maybe revisit some of the ideas from the 70s that largely formed the basis of the fall angle work previously. But that's certainly, I would say, took some time to come problem rather than something we can address directly, just because it's not a first order measurement, it's a correlated measurement. We also hope to be able to link this up with a lot of the radar products, which have things like wind velocities and trajectories through the storm, so we can sort of better understand how these hailstones are actually moving through. And I think that will provide some insight into the potential range of fall angles.
I completely agree with everything John said. He mentioned tumbling. I will just note that up until maybe a year or two ago, there was still a whole lot of debate in the hail community over whether hailstones did tumble when they fell. And so now that we've got ICECHIP, yeah, they tumble when they fall. So we've been able to successfully conclude a few things here.
Fantastic. Well, perfect. We do have some questions from the audience, so we'll transition into that. We've got about 10 minutes left, so we should be able to get to a few of these. First one here is from Lindsay. How can this work improve hail risk maps to inform strategic decisions made on equipment selection by solo developers? So we know there's a bias in spotter observations towards more populated areas. Can this work help to improve the public data that developers leverage to be more accurate in rural areas of the country?
The answer, I think, simply is yes. How, I think, is a little bit more complicated because there's a lot of ways to generate hail risk maps. One of the big things for ICECHIP was trying to marry up really high quality surface observations and radar. A lot of risk maps have a radar product involved in them. They're based on relationships that were fitted on a relatively limited sample. They didn't have the spatial fidelity that a lot of the observations during ICECHIP did. Because we've also got sensors that are time sensitive, we can actually match those straight up to the radar and be able to look and say, hey, can I get a better idea of what this storm was producing? So for locations outside of populated areas, I think that's going to have a significant implication. Now it's probably a few years away, and it's reprocessing existing data sets and all sorts of things like that it's going to translate there. But I think that's going to be one of the implications. I think the other implication is thinking about how much under a storm the coverage matters, right? So here we're looking at the hail swath in great detail. There's sort of been an assumption that, hey, if I've got a mesh value or I've got an point observation, that's representative of the storm. The amount of variation we're seeing across the swath, how narrow the windows might be for some of the larger stuff that is PV relevant, or particularly for some of the more hardened modules, I think is something where we're, I think, able to make a contribution and sort of think a little bit more about, how extensive is really the point risk if I'm exposed to a storm, right? So, am I worried about a horizontal scale of 1 kilometer, or am I worried about a horizontal scale of several kilometers? I think that's a relevant consideration.
Yeah, I completely agree. And I will note this is probably even further out than what John was describing, but we are hoping eventually of potentially being able to establish some connections between the variety of radar data and some of the non-size related hail characteristics, like maybe something like density, through getting an understanding of at least maybe the amount of supercooled water, or maybe seeing something about melting, wet covered stones, being able to pull some information about that from the radar, because as we all know, you've got to use some sort of remotely based or remote sensing based product in order to address those rural regions. So being able to provide any sort of information beyond size, is going to be helpful too.
Great. Thank you. I'm going to go to this question. I'm going to jump to this question from Steve. He says, thanks for the info. How likely is a storm to have a circular wind phenomenon or changing wind direction? And then actually, I'm going to follow that up with another question we have here about the connection between wind speed direction and storm direction.
Oh, Lord. Well, yes, the wind speed and direction across the storm varies. And the wind speed and the wind direction and the storm direction also vary and are not necessarily correlated one-to-one. For example, I don't mean to harp on this handy figure that's already up here, but since it's up here, these hailstones were all produced by a linear system that was propagating from northwest to southeast, its same direction throughout the entire sampling period across all 4 locations. And you can see the wind, the east dimension of the wind varied greatly. So it's not a simple matter.
Yeah, I think there's, that it really depends on the storm mode. And there are some where that storm is in its life cycle, when it impacts a plant, I think is going to be the real relevant question here. There are, the vast majority of storms that are producing our really large hail here have a circulation. And so therefore, because of that, we do have the potential that we would have various different orientations of wind field associated with that. Now, that's difficult to anticipate because it really does depend on which angle the storm approaches your site from and where it is relative to the storm overall. Realistically, it means that a preferential stow direction is probably unlikely to make that much, a massive difference, except in maybe some cases. The better option being that we have a stow direction, right? Because the wind field is potentially going to change anything that reduces that overall fall angle. The stronger winds aren't necessarily always associated with the storms that produce the largest hail sizes either. We've seen that previously, but there's a lot of variation there as well.
Great. I'm going to follow up with a quick question on that. We've talked some about wind speeds now during these events. Is there, what were some of the higher end velocities that you were getting out of the systems that we observed in the field last summer?
I can give a number on that. 44 meter per second at 1 meter above ground level. So
is that IOP 20?
Mm-hmm.
Okay. Yeah.
And in that case, we saw hail that was up to 3-inch diameters, and I think a little bit bigger than that as well. So we saw very, very substantial wind velocities in some of these cases. That sort of data has never been captured together before, and it's certainly something where we're looking to look more into some of these data. That's a very extreme case. That case went on to produce a derecho event across North Dakota. That was sort of the early stages of it. But we had wind measurements in close proximity. So that's the other thing. I think we sort of haven't mentioned this, but in addition to these impact astrometers, we had the portable mesonet pods, which are used for tornado deployments. So they're designed to be put in the path of a tornado and experience a tornado. So they weigh quite a bit. They're fairly heavy. They've got wind sensors on there. We did break a few wind sensors, but we got a lot of very, very high quality wind measurements in very close proximity to sort of better understand what the winds are associated with these events, particularly once we marry those up in terms of time steps.
Agreed. And I will just throw out there that I think it was 2 or 3 miles to the east of our main ground array, the hail size dropped down to like 25, 30 millimeters. So just to throw another complexity in the in the bucket. Yeah.
Well, great. We're almost at the top of the hour here, so I want to thank you both for your time and the willingness to share some of these initial results. I think this was really great, really informative. And yeah, thank you all for attending today's webinar on Project ICECHIP. And with that, I will close.
I will just note, and I'm sure this is the case for John as well, but if anyone has any questions for us, I think David's got our emails, so we'd be happy to talk further.
Wonderful.
Thanks.
All right. Thanks, everybody.